Welcome to MRS Bulletin's Materials News podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Laura Lay. Often, some of the most spectacular research starts out as an unfunded side project. A futuristic settlement on the moon could be powered by photovoltaics, and current space-based endeavours use materials fabricated entirely on Earth. What if you could use materials found in abundance on the moon to fabricate solar cells? According to Dr. Felix Lang from the University of Potsdam in Germany, his collaborative side project has shown that the moon's own regolith could be melted into glass and used as a substrate for perovskite solar cells, saving 99% of transport weight when compared to transporting entire solar cells from the Earth to the moon. Lunar regolith found on the moon's highlands is mainly composed of anorthosite, rich in calcium and aluminium with a small amount of impurities. It forms a brown-tinted glass with about 60% light transmission. Basaltic regolith is found in the lowlands, which is richer in iron and magnesium and melts to form a pitch-black glass. This basalt-based glass is suitable for the backside of the solar cell, whereas the anorthosite-based glass can be used as the top layer.
We were afraid of dirt coming out of the regolith or of the moon glass and going into our perovskite, especially because we wanted to use the regolith without any purification. This was our vision. It turned out to be not a problem at all.
The dirt Dr. Lang mentions includes elements such as calcium and iron, which could introduce defects in the perovskite structure. The iron content proved to be beneficial. When the moon glass was exposed to high-energy proton beams, a simulation of the intense radiation fields encountered in space, they found that the iron acted as a defect sink, preventing the glass from discolouring. Glass often discolours when exposed to ionising radiation, which reduces light transmission and so could be detrimental to power production. Perovskites are often unstable on Earth due to environmental effects such as moisture and oxygen. The same properties that make perovskites unstable also make them radiation tolerant.
We have some radiation in space really kicking out one atom from its initial position to some other place where it's a defect, right? Where it's a defect and you lower your performance of the solar cell. So this happens also in the perovskite, but then the perovskite crystal itself has a lot more flexibility. I always like to draw this association, but maybe it's also exaggerating a little bit, of like a jelly. So all these atoms are at their positions, but they can also wobble around. They have some freedom. And actually in the perovskite, ions can move around relatively easy. So when you now have radiation, you can kick out one atom, but this atom also can come back to its original position.
The team developed various ways to fabricate the solar cells. For the pitch-black basalt-based moon glass, top contacts made from either a transparent layer of sputtered indium zinc oxide or an ultra-thin semi-transparent metal contact comprised of nanometer layers of copper, silver, and molybdenum trioxide were used. Where the anorthosite-based semi-transparent moon glass is used as the top layer, copper was used as a bottom contact.
We wanted to show that we can adapt the architecture for the type of glass and the type of regolith we want to use on the moon.
Power conversion efficiency was around 10%, with some device architectures leading to improved efficiencies of around 12%. This might seem low for a perovskite-based device, but for space applications, one important parameter is power production per gram of material sent to the moon. Although some components will need to be transported from Earth, calculations showed that using the moon glass resulted in a power-to-weight ratio that outclassed other technologies, even with the lower efficiency. Future work will look to improve this efficiency by considering tandem solar cells. Since the moon glass also absorbs some energy, a simple solution to remove the iron using magnetic separation was proposed. What started out as a collaborative side project between perovskite specialists at the University of Potsdam and the Space Exploration Group at the Technical University Berlin in Germany, that was completed over several years, marked an interesting first step to fabricate devices on the moon. This work was published in a recent issue of Device. My name is Laura Lay from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org. Follow us on Twitter at MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.